a few code snippets. Yeah, that's not really interesting. Drop your group and user IDs. Be sure to drop the group before the user ID, because otherwise you may not have the permissions anymore. Then, what's also very important about change root doesn't really work unless you change your current working directory to the change root directory. You always need to care about this. So either you do it this way or you do the change root first and then a change directory /. And as you can see here, always check about return values. Actually, this code is quite boring, but that's the simplest way to show this all. The communication between the two child processes, well, as I said before, it's quite boring code. But what we always checked was that certain sizes were not overrun, so that no buffer flow of any kind can happen, and that's really crucial, because that's really one of the attackable parts. So you need to get that right. So design your communication protocol as simple as possible. A few more words on resource limits. What we did was we limited the maximum CPU time that the child process may use to 2 seconds. We found it to be enough. We limited to the maximum size of the data segment, the maximum size of the stack, the maximum size of the RSS, and the maximum real time. And that is really important, because that makes it really hard to take over the unprivileged process, which is in its change root environment, and use it for any long-running tasks. Even if it's unprivileged, and you can take it over and use it for a long time. You can use it for zombies, for botnets, because even then it's in the regular conditions allowed to bind to a high port and accept network connections. And that's why you need to enforce that, so that after 10 seconds the line is cut and the process dies. So that's how you can well, prevent that your unprivileged child process is used for any, yeah, for example, SETI at home, or as a zombie for a botnet, or any other distributed computing effort. Again here, the set R limit. It provides quite a few options what you can do. And the best advice for the values that that we use is that you should use is just experiment. It's really difficult to find it out, and experimentally we found out that the values we used worked good enough. We had some issues with GNU-TLS, because we support both OpenSSL and GNU-TLS as SSL library, and GNU-TLS requires a lot more resources. So it has a minimum requirement of something like 32 file descriptors, and we needed, I think, 8 seconds of CPU time, because it does some really weird stuff like busy waiting. So it really takes up a lot of CPU time. And this whole principle with putting an unprivileged process into a change root environment and having it communicate with a privileged process is called privilege separation. Well, you're using the unprivileged process is, of course, unprivileged. It means it has a user ID and group ID of greater than 0. It's in a change root environment. Resource limits are enforced. It directly communicates with the client, and the client is the attacker or potential attacker. And it also communicates with the privileged process. But the privileged process only does the few things that really need higher privileges than the completely unprivileged process. So usually these aren't a lot of operations. In our case, it was only the checking of the magic cookie and running the command, calling the IP tables binary. Yeah, as mentioned before, this concept is called privilege separation. It was first described in a really good paper with the title Preventing Privilege Escalation by Niels Provos, Markus Friedl, and Peter Honeyman. And the first implementation was OpenSSH. And OpenBSD, in its effort to improve overall security, implemented this concept of privilege separation in virtually all servers they provide, like NTPD and syslog daemon. And it seems to work, and it's quite cheap to get a lot better security. So it doesn't take a lot more resources compared to other means of defeating attempts of attack. Yeah. Another important thing are implementation errors in SSL and TLS. This is something that people usually do not really care about, because it's a piece of software, black box, just a library that you use and that's supposed to work. But SSL, TLS implementations have been shown to be vulnerable in the past, and that's why an attack against the SSL implementation is really likely. I found a few numbers, and the Secunia, this, I think, Swedish security company, they have 11 OpenSSL advisories from a time span from 2003 to 2006, so that's quite a lot. And the US CERT, Department of Homeland Security, has 21 OpenSSL related and 4 GNU TLS related vulnerabilities in the last 3 years. So SSL is really something that is quite likely to be attacked. So you need to care about it. And so we looked at how you usually implement SSL and found quite a simple solution. Because usually you first read keys and certificates from the file system. You initialize the SSL subsystem. It does, let me see, it loads error strings, you add algorithms and other fancy stuff. Then we enter the change root environment and drop all privileges. And then we initialize the actual SSL connection. And that's the point where the attacker is first able to interact with us at all. So the first contact, the first interaction is already in a secure environment. And as mentioned before, Chapter 2 supports both OpenSSL and GNU TLS in order to provide an alternative in case one of the two has been compromised. So I told you the numbers before, it's quite likely, and when you see shit, an unpatched OpenSSL vulnerability, let's switch to GNU TLS. Although the code quality of GNU TLS in some parts is quite dubious, so I wouldn't really recommend it. But after all, there aren't that many SSL implementations out there, especially not for Unix-like systems. So OpenSSL is really standard. yeah, just a short code snippet. We have this init SSL, which does all the fancy stuff, as mentioned before, load error strings, add SSL algorithms, create the SSL context, loads the certificate, private key, and all that stuff. And the init SSL2, which happens after dropping the privileges, associates the file descriptor with the SSS handler that you need to communicate via SSL. And then it accepts the SSL connection. The third problem we came upon was denial of service. We identified two main points, namely denial of service attacks against system logging, when in the very unlikely case that you do take over process, that you run an attack against system logging or run an attack against forking, basically connecting a really lot of times during a very short period of time, because too many connections per time frame lead to too many processes and too much system load, and your system may become unusable for users that actually should use it. So in the case an attacker really is able to take over an unprivileged child process, the hard disk could be filled up by when you're running thousands of syslog calls per second. And to slow down such an attack, the number of syslog messages per time frame is simply limited. It's quite simple, and it has the disadvantage that we implemented only a wrapper around the syslog system call called limit syslog, and when some exploit code runs the syslog system call directly, that doesn't quite work. So the syslog daemon actually has to care about this too, but it's not such a great threat anyway. It's only for the situation when, for example, exploit code calls parts of our own code, which very often does syslog calls, and so that's where the limit syslog comes into effect. And here, the more interesting stuff, credits for this go to Clifford only, because he's the one who developed it, and it's quite simple and quite effective. Yeah, the basic problem is that when you have too many connections per time frame, it leads to too many child processes. In the drawing before, one connection leads to two child processes, so that's quite a lot of resources. And of course, too much system load, your system may become unusable. So you need to limit the incoming connections per source IP. Plus the number of incoming connections at all. But chapter 2 should still be functional and responsive for users from other IP addresses. And that's how we implemented our countermeasure. We used the source IP from the client plus a random value, which changes every 8 seconds. We hash this and divide this by the number of slots and take the remaining part. And this is the slot number. And for every slot, the number of connections is counted per time frame. If the count is higher than a certain threshold, then the request is simply rejected before even the fork is going to happen. And after every time frame, these 8 seconds, the counter is reset and the random value changes. The number of slots is currently 397,